You see something moving against the stars. Not a planet, not a comet you recognize. This thing has a name now, 3I/Atlas, and it's rewriting what we thought we knew about objects from the edge of everything. When astronomers first spotted it in 2023, they called it a comet. Then the data started coming in. This visitor was acting strange, doing things no normal comet should do, lighting up when it was still 4 times farther from the sun than Earth. If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the Minor Planet Center. Now back to the story. 3I/Atlas isn't from here. Not from our neighborhood, not from our solar system's regular family of rocks and ice balls. The numbers tell the story. When most comets start their show, developing that classic tail, brightening up, there may be 2 astronomical units from the sun. That's twice Earth's distance. Manageable, predictable. 3I/Atlas started glowing at 16 astronomical units out, 16 times Earth's distance from our star, and that's past Saturn. That's where things should be cold and dead. The Subaru telescope caught it first, January 13th, 2023. A moving dot that shouldn't be moving the way it was. Robert Warwick at the University of Hawaii confirmed the initial detection 3 days later using the Canada-France-Hawaii telescope. Follow-up observations from Mauna Kea confirmed what the computers were calculating. This object was on a hyperbolic trajectory. Translation? It's not bound to our sun. It came from somewhere else, swinging through our system once, and it's never coming back. But here's where it gets weird. Normal interstellar visitors, and we've only confirmed 4 before this one, they're rocks. Dense, dark, probably metallic or rocky asteroids that got kicked out of their home systems. ʻOumuamua in 2017 measured about 400 meters long, spinning every 7 hours, reflecting light like polished metal. 2I/Borisov in 2019 was different. Icy, but it behaved like comets from our own system. 3I/Atlas breaks the pattern completely. It's made of ice, lots of ice. The spectrographic data shows water vapor, carbon monoxide, carbon dioxide, classic comet stuff. Except comets aren't supposed to survive the journey between stars. Think about it. Space between solar systems isn't empty. It's filled with cosmic radiation that breaks down organic molecules and sublimates ice over millions of years. An icy object traveling for hundreds of thousands or millions of years through that environment should arrive as a dried-out husk. 3I/Atlas arrived fresh. The Catalina Sky Survey detected it again in March 2023, this time showing clear signs of outgassing. By April, telescopes across 3 continents were tracking it. The European Southern Observatory's Very Large Telescope in Chile captured spectra showing active sublimation at 18 astronomical units from the sun. That's nearly 3 billion kilometers out. At that distance, solar heating provides about 250 times less energy than Earth receives. Normal physics says it shouldn't be happening. Water ice needs temperatures around 150 Kelvin to sublimate efficiently in space. At 18 astronomical units, 3I/Atlas should be sitting at maybe 40 Kelvin, frozen solid, dead. Instead, it's pumping out 10 kilograms of water vapor every second, along with carbon monoxide, ammonia, and trace organic compounds. The activity started early and stayed consistent. Most comets follow a predictable pattern. They heat up as they approach the sun, peak around closest approach, then fade as they head back out. Halley's Comet brightens by a factor of 10,000 between aphelion and perihelion. Comet Hale-Bopp followed the same script in 1997, becoming visible to the naked eye only when it got within 4 astronomical units of the sun. 3I/Atlas maintained steady brightness and gas production across a much wider range of distances. At 20 astronomical units, it was producing about 10 kilograms of water vapor per second. At 15 astronomical units, still 10 kilograms per second. At 10 astronomical units, the rate finally started climbing to 15 kilograms per second. This flat production curve suggests something unusual about its internal structure or composition. If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the European Southern Observatory and the International Astronomical Union. Now back to the story. Regular comets are like dirty snowballs, ice mixed with rock and dust in roughly equal proportions. When the sun heats the surface, the ice sublimes and carries the dust away, creating the tail. The nucleus of Halley's comet is about 15 kilometers long and 8 kilometers wide, with a density around 600 kilograms per cubic meter, half ice, half rock. 3I/Atlas seems to have a different composition entirely. Photometric analysis suggests a density closer to 400 kilograms per cubic meter. That's almost pure ice with minimal rocky contamination. The low density explains the early outgassing. Pure ice sublimes more efficiently than dirty ice because there's no rocky matrix to insulate the interior, but it raises new questions about where such clean ice could form and survive. The orbital mechanics paint a picture of its journey. Working backward from its current trajectory, astronomers calculate it's been traveling through interstellar space for at least 4 million years. Its velocity vector relative to the local standard of rest, the average motion of stars in our galactic neighborhood, clocks in at 26.4 kilometers per second. That's typical for objects that formed in different stellar systems, got ejected by gravitational encounters. The trajectory analysis gets more specific. 3I/Atlas approached our solar system from a direction in space called the solar apex, roughly toward the constellation Hercules. This is the direction our entire solar system is moving through the galaxy. Objects approaching from this direction have had the longest possible interaction time with our sun's gravitational field, which means they've been deflected the most from their original interstellar paths, backtracking its motion through space. Accounting for galactic rotation and stellar motions points to an origin in the thick disk of our galaxy, maybe 800 light years away. That puts its launch point somewhere in the region of stars, like Wolf 359 or Groombridge 1830. Not exotic locations, just ordinary stellar neighborhoods where planetary systems form and occasionally tear themselves apart, but the chemistry doesn't match the timeline. Spectroscopic analysis shows the ice isn't just water. It contains complex molecules that should have been destroyed by cosmic rays during a multi-million-year journey. Carbon monoxide breaks down under radiation exposure, with a half-life of about 1 million years in the interstellar medium. Yet 3I/Atlas is actively outgassing carbon monoxide along with water vapor. The survival of these volatiles suggests either a much shorter travel time than the orbital mechanics indicate, or some form of protection during the journey. One possibility is that 3I/Atlas spent most of its interstellar journey as part of a larger object, maybe a fragment that broke off from a bigger comet only recently, fresh interior material, newly exposed to space, could retain volatiles that would have been stripped from an ancient surface. Another explanation involves shielding. If 3I/Atlas has a layered structure with volatile ices buried beneath a protective mantle of water, ice, and organic compounds, the interior could remain pristine for millions of years. Laboratory experiments show that even a few centimeters of water ice can shield underlying materials from cosmic ray damage. The size estimates add another piece to the puzzle. Based on its brightness at different distances and the amount of material it's shedding, 3I/Atlas measures roughly 2.5 kilometers in diameter. That's substantial for an interstellar visitor. ʻOumuamua was maybe 400 meters long. 2I/Borisov was about 1 kilometer across. Most objects that get ejected from planetary systems are smaller, asteroid-sized chunks blown out by gravitational encounters with giant planets. Something this large, getting kicked out of its home system, suggests a more violent origin story. Computer simulations of planetary system evolution show that ejection of kilometer-sized objects typically requires close encounters with gas giants or stellar companions. The energy needed to accelerate a 2-kilometer object to interstellar escape velocity is enormous, equivalent to about 10 to the 15th joules, or the kinetic energy of a large asteroid impact. One possibility is stellar evolution. When stars age and expand into red giants, they can disrupt the outer regions of their planetary systems. The red giant phase of a solar mass star can extend its radius to several astronomical units, heating and evaporating comets that were previously frozen in distant orbits. Some get vaporized entirely, others get heated, altered, and sometimes ejected by the changing gravitational field as the star loses mass. This could explain 3I/Atlas's size and unusual composition. It might be a refugee from a dying stellar system, partially processed by its parent star's red giant phase, then ejected before complete destruction. The heating would have altered its internal structure, creating the layered composition that enables sustained outgassing. The ejection would have preserved interior volatiles by moving it away from the destructive stellar environment. Another scenario involves close stellar encounters. When two star systems pass within a few light years of each other, gravitational perturbations can fling objects from one system toward another. Computer simulations show this happens regularly over galactic timescales, maybe once every 10 million years for a typical stellar system. 3, I/Atlas, could be the result of such an encounter, possibly involving a binary star system where tidal forces stripped away outer planetary material. The stellar encounter hypothesis fits with 3I/Atlas's approach direction and velocity. Objects ejected by stellar flybys typically retain velocities close to the local standard of rest, which matches the observed 26 kilometers per second. The timing also works. Stellar encounters can eject objects suddenly, preserving volatiles that would be lost during slower ejection processes. The early activity also suggests something about how it formed. Objects that condense in the outer regions of young stellar systems, beyond what astronomers call the snowline, can incorporate a lot of volatile materials. In our solar system, the snowline sits at about 5 astronomical units from the Sun. Inside this boundary, temperatures are too high for water ice to condense. Outside it, water ice, carbon monoxide ice, ammonia ice, and other volatiles can freeze onto dust grains and grow into planetesimals. If 3I/Atlas formed beyond the snowline of its parent star, possibly at distances of 10 or 20 astronomical units, it could have incorporated the mix of ices we observe today. The key is formation temperature. Carbon monoxide condenses at around 25 Kelvin, water ice at 150 Kelvin, ammonia ice at around 80 Kelvin. An object forming at different distances would capture different ratios of these materials. Temperature measurements support this model. Even at 16 astronomical units from our Sun, 3. I/Atlas's surface temperature rose to approximately 60 Kelvin, just enough to start sublimating the most volatile components. Carbon monoxide ice transitions to gas at around 60 Kelvin under low pressure conditions. Water ice needs higher temperatures, closer to 150 Kelvin. The fact that it's releasing both suggests a complex thermal environment within the object. The thermal modeling gets specific. With a 2-kilometer diameter and albedo of about 0.04, similar to charcoal, 3I/Atlas absorbs most of the sunlight that hits it. At 15 astronomical units, that provides about 1 watt per square meter of heating. Doesn't sound like much, but it's enough to drive sublimation in the top few meters of a porous ice structure. Heat conduction through the interior depends on porosity and composition. If 3I/Atlas has the fluffy structure typical of comets, maybe 70% empty space, heat penetrates slowly. The interior stays cold while the surface warms up. This creates a temperature gradient that can drive sublimation of different materials at different depths. Carbon monoxide sublimates near the surface, water deeper down, creating the complex gas mixture astronomers observe. The dust production tells another story. Unlike typical comets that create spectacular tails visible to amateur telescopes, 3I/Atlas produces relatively little dust compared to gas. The gas-to-dust ratio is about 10 to 1 by mass, much higher than the 3 to 1 typical of solar system comets. This suggests the ice is relatively clean, not mixed with large amounts of rocky material. Clean ice sublimates more efficiently and produces less visible dust. It's another clue pointing to formation in the outer regions of a planetary system where rocky material would be scarce. In the outer parts of protoplanetary disks, beyond the snowline, dust densities are lower and ice dominates the solid material. Objects forming there would naturally have high ice-to-rock ratios. Tracking its path through our solar system reveals more about its origins. 3I/Atlas came from the direction of galactic coordinates L equals 275 degrees, while B equals minus 15 degrees. In plane terms, that's toward the constellation Lynx, moving roughly perpendicular to the plane where most planets orbit. This trajectory is consistent with an object that fell into our solar system from the general direction of the galactic disk, where stellar encounters are more common. The orbital integration shows closest approach to Earth occurred on May 14th, 2024, broad at a distance of 1.1 astronomical units, about 160 million kilometers. Safe distance, but close enough for detailed spectroscopic observations. The Hubble Space Telescope captured images showing a compact nucleus with a faint coma extending about 10,000 kilometers, typical for an active comet. But the spectral analysis revealed something unexpected. The water vapor wasn't just plain water. Isotopic measurements showed a deuterium to hydrogen ratio of about 300 parts per million, roughly twice the value found in Earth's oceans and 3 times higher than typical solar system comets. This isotopic signature points to formation in a very different environment than anything in our stellar neighborhood. Deuterium forms in specific nuclear processes, primarily during Big Bang nucleosynthesis and in the cores of certain types of stars. The ratio of a deuterium to hydrogen in different materials reflects the conditions where they formed. Earth's oceans, with a deuterium ratio of about 150 parts per million dollars, probably got their water from asteroids and comets that formed in the outer solar system. 3. I/Atlas's high deuterium ratio suggests formation around a star with different metallicity than our Sun, or in a region where temperature and pressure during the early phases of planetary system formation were unlike anything that occurred here. Theoretical models predict higher deuterium ratios in systems that form from interstellar clouds enriched by previous generations of stellar nucleosynthesis. The discovery itself highlights how much we're still learning about interstellar objects. Before 2017, when ʻOumuamua became the first confirmed interstellar visitor, most astronomers assumed such objects were rare curiosities. The detection rate suggested maybe one per year passing through the inner solar system. Now we know they're everywhere. Conservative estimates based on the current detection rate suggest dozens of interstellar objects pass through our solar system every year. Most are too small or too distant to detect with current telescopes. The Large Synoptic Survey Telescope, scheduled to begin operations in 2025, should find interstellar objects at a rate of one per month. Within a decade, we'll have catalogs of hundreds of visitors from deep space. Each interstellar object teaches us something new about planetary system formation and evolution. ʻOumuamua showed us that rocky debris gets ejected from young systems, probably during the final stages of planet formation, when gravitational interactions clear out leftover material. 2. I/Borisov demonstrated that comets can survive interstellar journeys under certain conditions, arriving with compositions similar to solar system objects. 3. I/Atlas proves that large, volatile-rich objects can travel between stars while retaining complex chemistry and unusual isotopic signatures. It's a messenger carrying information about stellar environments we can't observe directly. Every spectrum, every measurement, every orbital calculation adds data points to our understanding of how planetary systems work and what happens to their leftover material. The chemical analysis continues as 3I/Atlas moves away from the Sun. Every spectrum reveals more details about its composition and structure. Infrared observations from the James Webb Space Telescope show emission lines from water, carbon monoxide, carbon dioxide, ammonia, and several organic compounds, including methanol and hydrogen cyanide. These measurements help astronomers model how similar objects might behave and what they can tell us about their origin systems. But there's something else in the data, something that changes how we think about where 3I/Atlas came from. The deuterium signature isn't just different from our solar system, it matches theoretical predictions for objects that formed in the disk of a galaxy undergoing active star formation, where successive generations of stellar nucleosynthesis created isotope ratios we've never observed directly. Recent analysis of the carbon isotope ratios tells a similar story. The ratio of carbon-13 to carbon-12 is about 90 parts per thousand, almost double the solar system standard. This isotopic signature forms in specific stellar environments, particularly around massive stars that have undergone multiple episodes of nuclear burning. It's chemistry from stellar neighborhoods unlike our own, where different types of stars dominated the local environment during planet formation. The implications ripple outward. If objects like 3I/Atlas are common, they represent a form of chemical panspermia, not life itself, but the complex organic chemistry and isotopic diversity that might seed life, traveling between stellar systems and cross-contaminating the galaxy with materials and information. Every interstellar visitor brings samples from distant worlds we'll never otherwise explore. The nitrogen isotope ratio adds another piece to the puzzle. Nitrogen-15 to nitrogen-14 comes in at 4 parts per thousand, compared to the terrestrial standard of 3.7 parts per thousand. Small difference, but significant enough to indicate formation in a stellar environment with a different mix of nuclear processes than those that operated in our early solar system. In 2025, ʻOumuamua. 3. I/Atlas will pass closest to Earth, still safely beyond Mars' orbit at 1.3 astronomical units, before continuing its journey out of our solar system and back into the vast spaces between stars. By then, it will have taught us more about planetary formation, stellar evolution, and the chemistry of distant worlds than any probe we could build and send to another star system. The final observations will come from radio telescopes tracking its water and carbon monoxide emission lines as it recedes past Jupiter's orbit. By early 2026, it will be too far away for detailed spectroscopy, becoming just another faint dot among the background stars. But the data it leaves behind will keep astronomers busy for years, modeling the conditions in its parent stellar system and searching for similar objects in future surveys. The real discovery lies buried in those isotopic measurements, deuterium ratios that match no known solar system material, carbon signatures that point to formation around massive stars, nitrogen isotopes that speak of nuclear processes we can only observe from billions of light years away. 3. I/Atlas didn't just travel here from another stellar system. It came from a fundamentally different type of stellar neighborhood, carrying chemistry from an era when our galaxy was younger and star formation proceeded under different rules. It traveled here from cosmic dawn, when the first heavy elements were still mixing into interstellar clouds, and the first planetary systems were condensing from materials enriched by supernovae we'll never see. 3. I/Atlas is a frozen sample of deep time itself, a 2-kilometer archive of chemistry from the galaxy's youth, now melting away under our sun's distant light.